Hi, my name is Prof. James. Welcome to this journey through space. Today, we are going to study the chapter, which is Computational Fluid Dynamics, CFD, for aerospace flows. In this chapter, we'll explore how CFD helps us understand aerodynamic flows, including the complex behavior of airflow over aircraft components like wings, fuselages, and control surfaces. By using CFD, engineers can simulate real-world fluid dynamics in a controlled virtual environment, optimizing designs and ensuring safety and performance without needing to conduct physical testing. Let's dive into the principles of fluid dynamics and how CFD plays a crucial role in modern aerospace engineering. Fundamentals of fluid dynamics. Fluid dynamics is the study of the motion of fluids, liquids, and gases, and the forces acting on them. The continuity equation ensures the conservation of mass in fluid flow, stating that the mass entering a system must equal the mass exiting it. The Navier-Stokes equation represents the conservation of momentum, describing how the velocity field of a fluid evolves under the influence of forces like pressure and viscosity. The energy equation is based on the first law of thermodynamics, governing the flow of energy within a system, including internal energy, work, and heat transfer. Fluid properties such as density, viscosity, and compressibility dictate how fluids behave under different conditions and are essential for accurate CFD simulations. These equations form the mathematical foundation of CFD and are used to simulate airflow around aerospace structures from subsonic to hypersonic flight. Numerical methods in CFD relies on numerical methods to solve complex fluid dynamics equations. The discretization process involves converting continuous differential equations into algebraic equations that can be solved iteratively. Convergence checks are performed during simulations to ensure that the solution is accurate and stable as the algorithm progresses. The choice of solver algorithm, e.g., steady state versus transient, explicit versus implicit, impacts the efficiency and accuracy of the CFD results. Iterative solving involves refining the solution step by step until the error between iterations falls below a specified threshold. By using these numerical methods, CFD can simulate real-world fluid behavior, even for complex geometries like aircraft wings and engine nacelles. Introduction to CFD software. Various CFD software packages are available for solving aerospace flow problems. OpenFOAM is a highly customizable open-source CFD toolkit widely used for research and industry applications. It uses a command line interface and offers a vast library of solvers for different flow regimes. Aerospace. Fluent is a commercial software package known for its user-friendly graphical interface and comprehensive physical models. It also includes automated meshing tools to streamline the simulation process. Both platforms allow simulation of subsonic, transonic, and hypersonic flows, with specialized models for turbulence, combustion, and multi-phase flows. OpenFOAM is favored for its flexibility and cost-effectiveness, while Aerospace Fluent is known for its robust technical support and ease of use. As engineers, understanding both tools allows you to choose the best one based on the project requirements, balancing flexibility, user-friendliness, and computational power. CFD workflow. The CFD workflow involves several key steps to ensure accurate simulation results. Geometry creation. The first step is creating a CAD model of the structure, such as an aircraft wing or fuselage, which will be analyzed. The geometry can either be created from scratch or imported from existing designs. Mesh generation. The geometry is discretized into smaller computational cells, forming the mesh. A fine mesh is critical around regions with high gradients, such as boundary layers and shock waves. Physics setup. Defining boundary conditions, e.g., inlet velocity, pressure, or temperature, and fluid properties, e.g., viscosity, density, and turbulence models, is essential for a successful simulation. Solving. The simulation is run using the selected solver, where iterations are performed until the solution converges to a stable state. Post-processing. The results are visualized, allowing engineers to analyze flow patterns, pressure distributions, and aerodynamic forces to make informed design decisions. Mesh generation fundamentals. Proper mesh generation is critical to the accuracy of CFD simulations. Cell quality metrics like skewness and aspect ratio affect the accuracy of the solution. Cells should be as equilateral as possible for optimal performance. Boundary layer resolution is crucial for predicting skin friction and heat transfer accurately. The Y+ values help define the mesh near the surface to resolve the boundary layer properly. Mesh-independent studies are conducted by running simulations with progressively finer meshes to ensure that the results don't change significantly with further refinement. Structured versus unstructured meshes. Structured meshes are typically used for simpler geometries, while unstructured meshes are better suited for complex geometries. A good mesh should balance accuracy and computational cost. Engineers must use hybrid meshing techniques to create optimal meshes in regions with high gradients or complex flow features. Turbulence. Modeling turbulence is a complex phenomenon that needs to be modeled accurately for reliable simulations. RANS models, Reynolds Averaged Navier-Stokes, are the most commonly used in engineering applications. These include KE and KO models, which approximate turbulent flow behavior. The Spalart-Allmaris model is a one-equation model commonly used for aerodynamic applications, such as external flow around aircraft. LES, Large Eddy Simulation, resolves large-scale turbulent eddies and provides higher fidelity but is more computationally expensive. It is typically used in separated flow regions or high-fidelity research simulations. DNS, Direct Numerical Simulation, resolves all turbulent scales, providing the most detailed information, but it is computationally prohibitive for most practical engineering applications. Turbulence modeling helps engineers predict drag, heat transfer, and flow separation, all of which are crucial for the performance and efficiency of aerospace systems. Flow over airfoils. Simulating flow over airfoils is a central application of CFD in aerospace. Pressure distribution across the airfoil surface is critical for calculating lift and understanding the aerodynamic characteristics. The boundary layer development on the airfoil surface influences drag and heat transfer. As flow transitions from laminar to turbulent, skin friction increases. Separation occurs when adverse pressure gradients cause the airflow to detach from the surface, leading to drag increase and potential stall. Stall characteristics and critical angles of attack can be predicted by CFD, helping engineers design airfoils with better stall resistance and optimize performance. By simulating airflow, CFD allows engineers to visualize pressure distributions, separation points, and other critical flow features, which are difficult to measure in wind tunnels. Compressible flows and shock waves. CFD plays a key role in understanding compressible flows and shock waves at high speeds. Compressibility effects become significant above Mach 0.3, where density variations can no longer be neglected and pressure waves interact with the flow. Shock waves form when an object travels faster than the speed of sound, creating discontinuities in flow properties such as pressure, temperature, and density. Normal shocks are perpendicular to the flow, while oblique shocks form at an angle, typically at sharp corners or leading edges. Expansion fans are regions where the flow expands and accelerates, typically seen in supersonic flow past curved surfaces. Understanding shock boundary layer interactions is crucial for aerothermal design in hypersonic vehicles and rocket nozzles.